My name is Tatiana Munoz, and the topic that I have chosen for my seminar presentation involves an analytical method known as Shpol'skii spectroscopy, and in this case, Shpol'skii spectroscopy for the analysis of polycyclic aromatic hydrocarbons, better known as PAHs. So a quick overview of the topics I will cover. First, I'm going to go over polycyclic aromatic hydrocarbons and what they are and some of their sources, as well as introduce the 16 EPA priority pollutant PAH compounds. This will lead into chromatographic methods for the analysis of these PAH compounds, and these include HPLC coupled to UV vis and fluorescence detection, as well as a GC mass spectrometry method. And then I will lead into Shpol'skii spectroscopy, a little bit about the phenomenon behind this method, experimental procedures involved in this method, and the instrumentation used for these measurements. And then I will finish off with an application of Shpol'skii spectroscopy, which involves the analysis of structural isomers of high molecular weight PAHs. So polycyclic aromatic hydrocarbons, better known as PAHs, are hydrocarbons or organic compounds which involve multiple fused aromatic rings, as can be seen here by these few examples. Naphthalene being the simplest PAH, which is two benzene rings fused together. These are a large class of environmental pollutants that are really found everywhere and are continuously appearing. And they are known to be toxic, mutagenic, and carcinogenic, being that benzene is the building block of these molecules, which is a known carcinogen. A couple of sources of PAHs include natural and anthropogenic sources. Among the natural sources would be things like forest fires, even volcanic eruptions, and petroleum seeps from the ground. All of these would contribute to PAHs in the environment. And then anthropogenic sources would include emissions from the combustion of fossil fuels, such as those emissions from cars, the emissions from using those same fossil fuels as energy, which can be portrayed here, and something as typical as the high temperature grilling of meats also develops these PAHs. But the main commonality between these two main sources is that they involve the incomplete combustion of organic material. Being that these PAHs are found worldwide everywhere and ever increasing, the United States Environmental Protection Agency, or the EPA, has created a list of 16 PAH compounds for the routine analysis, and they're on the priority pollutants list. And this list includes from the simplest PAH naphthalene with a molecular weight of 128 daltons, all the way to dibenz AH anthracene, which is at 278 daltons. So all of these PAH compounds have been selected by the EPA to be routine analyzed. Being that the EPA chose these compounds for analysis, they've also developed several chromatographic methods for these analysis, one of which includes EPA method 550.1, which involves the chromatographic analysis of PAHs in drinking water. And this method actually involves liquid-solid extraction to begin with. So a liter of sample is passed through a solid inorganic matrix cartridge coated with a C18 organic phase. The sample would be eluted with methylene chloride and later reconstituted. So it would be dried to 1 milliliter, a couple of milliliters of acetonitrile is added, and then the final volume of the sample that will be injected into the HPLC will be about 0.5 milliliters. The HPLC itself is a reverse phase chromatography is used in this case with an acetonitrile mobile phase coupled to UV absorption and fluorescence detectors. So this list here is just a list of the target analytes for this method, which, as you can see, include the 16 EPA PAHs, and is shown by the sample chromatogram here, which is measuring absorbance and retention time. There is a successful amount of separation with this method for all 16 of these analytes, and therefore it would be successful for the determination and quantification of these EPA PAHs. In addition, the EPA has developed a GC method, or gas chromatographic method, which is similar except it involves solid phase extraction. So 1 liter of sample fortified with surrogate analytes, which are actually used to determine the efficiency of the extraction by this method. This is eluted with an organic solvent depending on which target analytes are in your sample. Again, reconstitution, so the solvent is dried through an anhydrous sodium sulfate column, evaporated by a gentle stream of nitrogen gas till dryness, and then internal standards are added, and later the sample is adjusted to 1 milliliter volume with ethyl acetate. And this is actually the sample that's injected into the GC via a splitless injection. And the column is a high-resolution fused silica capillary column interfaced to a mass spectrometer. This method actually includes several more target analytes than the previous method. It's a very long list. This is just a small portion of the list that includes some of those EPA PAHs. However, the entire list itself does include all 16. So all 16 of those PAHs can be separated via this method. And here's another sample chromatogram including these analytes listed here, and as you can see, the separation is successful. Not quite as clear as the previous, but still satisfactory in order to be able to identify these PAHs, these 16 PAHs. So leading into Shpol'skii spectroscopy, although the methods talked about before are good for separating and identifying those 16 EPA PAHs, that list does not include thousands of PAH compounds, many of which cannot be separated via those chromatographic methods provided by the EPA. The reason for this is that room temperature luminescence spectroscopy techniques are often limited by unresolved band structure, so broad band structure. This is in part due to inhomogeneous band broadening, which is caused by various analyte microenvironments, or many of these PAHs in a sample are experiencing different microenvironments, and therefore this yields multiple bands. The band broadening limits the selectivity of these methods for specific PAH compounds in complex samples. So a solution to this would be Shpol'skii spectroscopy, which incorporates these molecules in a rigid matrix at low temperatures to minimize the band broadening, and these are known as Shpol'skii conditions. The requirements for this method include low temperatures, or less than 77 Kelvin, a rapid freezing rate of these samples, and a solvent host with a dimensional match, which I will go over in following slides, and low analyte concentrations at the parts per million level or lower. And this graphic here just represents a liquid nitrogen cryogen container, which is something that is commonly used to freeze these samples. So the Shpol'skii effect, a little bit about the phenomenon behind this method. The Shpol'skii effect can be described using an example. So if you take benzoyl apyrene, or BAP, and you rapidly freeze it in ethanol to about 10 Kelvin, the spectral bandwidths observed are about 500 centimeters to the -1, which is relatively broad. However, if you take this same PAH molecule and you rapidly freeze it in N-heptane, the spectra observed, or the spectral bandwidth observed, are what you call quasi-linear, or almost line-like, with as sharp as 10 centimeters to the -1. So we see the phenomenon described here is an increased resolution of this spectra correlated to the solvent geometry. This can be usually described by the key and hole rule. So when you take these pH molecules and you freeze them in these matrices, you get frozen polycrystalline matrices with highly structured orientation of PAH molecules in the solid solvent host. So the substitution of these polycyclic aromatic hydrocarbon molecules occur at very specific crystallographic sites. And as can be seen here in the figure, the N-heptane solvent freezes in lamellar planes, as can be seen here, and we would expect the PAH molecule to be randomly distributed throughout these lamellar planes of the solvent. However, this is not what we observe. we observe that it substitutes directly into the planes at very specific sites with the long axis of the paraffin chain along the long axis of the molecule. Due to this, spectral band broadening is minimized. So this is a key and hole effect where the solvent fits around, or better yet said, the PAH molecule fits around the solvent molecule in a very specific site. For this reason, spectral band broadening is minimized. We have minimized vibronic band broadening because this is a rigid matrix and these molecules behave as isolated molecules. Thermal band broadening is minimized because the temperature is so low, below 77 K, and the inhomogeneous band broadening is minimized as well because these PAH molecules are at specific sites and experience identical molecular fields or identical environments, so we don't get that continuum of bands. So this key and hole effect is very easily visualized with catacondensed aromatics, or these aromatics with linear benzene rings attached. As we can see here with naphthalene and pentane, we can see the geometric relationship between these, as well as anthracene with n-heptane and so on. This is very easily visualized why these work under Shpol'skii conditions. However, for pericondensed aromatics such as pyrene and pyrrolene, these solvents have been experimentally determined to be the best to provide the most linear-like spectra and are not as easily visualized. Here's just an example of dibenzofuran in hexane at 4K. This is the absorption spectrum. And as we can see here, the spectra is very quasi-linear or line-like with these very sharp bands which serve as a fingerprint for that specific PAH. A little bit about the experimental procedure in order to do Shpol'skii spectroscopy. The first step would be development of calibration curves. So stock solutions of PAHs in their appropriate N-alkane solvent host would be developed. At least 5 PAH concentrations are ideal to develop these calibration curves. So we would start with stock solutions that would be diluted down to these 5 concentrations. And samples actually need to be stored in the dark to prevent photo decomposition. Sample preparation would follow. So if you have an environmental sample, first it would be important to extraction and cleanup and then dilute it in the N-alkane of choice with the appropriate N-alkane. Synthetic mixtures can also be prepared in the lab in order to test this method. These synthetic mixtures can be separated by chromatographic separation, or RPLC. Usually they would be evaporated with nitrogen gas and then reconstituted in the correct N-alkane. It's important to mention that these PAH concentrations should be in the linear dynamic range of those previously developed calibration curves. One of the most important steps obviously would be the sample cooling. So usually these samples are held in copper sample holders, which are then immersed in liquid cryogen. Liquid nitrogen can achieve around 77 Kelvin, and then liquid helium would go even less temperature to about 4 Kelvin. And as mentioned, this is important to happen rapidly, a rapid freezing rate, and both of these methods provide sample solidification in less than 90 seconds. And then after the sample is frozen, it would be placed into the sample compartment of your analytical instrument of choice, whether you wish to measure absorption, UV vis, emission, fluorescence, or even fluorescence lifetimes. Okay. The instrumentation used for Shpol'skii spectroscopy includes commercial spectrofluorimeters or laser systems built in-house, the most common being commercial spectrofluorimeters. Commercial spectrophotometers will have all of the same compartments as a commercial spectrofluorimeter. You would have your excitation source. However, these would be equipped with fiber optic probes and a fiber optic mount for these low temperature measurements. So as we can see here, the excitation source would be directed into a fiber bundle, which would lead into this dewar with the cryogenic liquid. This is usually a copper holding here. The sample compartment would be here. The sample would be rapidly frozen, and then the fiber optic emission fibers would lead back to the emission monochromator and the detector. So many of the same pieces as a common spectrophotometer, just equipped for these low temperature measurements. Laser systems that are built in-house, I won't go into too much because they are very complex and are very unique to the analytes of interest. The main point here is that these involve a laser excitation source, which provides very, very specific lines of excitation for even more resolved spectra, or if you have a very complex sample with multiple PAHs and would like to excite at very specific wavelengths, then a laser system would be appropriate for such a use. An application of Shpol'skii spectroscopy includes the analysis of structural isomers of high molecular weight PAHs. These are PAHs of molecular mass greater than 300 daltons, none of which are included on that EPA list mentioned previously. The important thing about these high molecular weight PAHs is that they have increased persistence in the environment, being that they are larger and less water soluble. These PAHs tend to be more persistent in the environment. Many of these high molecular weight PAHs exhibit higher levels of toxicity than PAHs of lower molecular mass for the same reasons, and this includes those EPA PAHs. Very important to note is that the toxicity of these isomers varies from isomer to isomer. So here we have 10 isomers out of 23 possible for the molecular mass 302 daltons. Some of these PAH isomers are extremely toxic and carcinogenic, some are less, and others are not toxic at all. Therefore, if we have a complex mixture involving these PAH isomers, we have the need to be able to differentiate and selectively determine those more potent PAHs from those that are not as a health hazard. So we need to selectively identify and quantify individual isomers in complex samples, which we cannot do with those previously mentioned chromatographic methods provided by the EPA. Why can we not do this with the other analytical methods? Chromatography is challenged by similar chromatographic behaviors between these isomers, and we do experience co-eluting isomers in this case. As far as mass spectrometry, since they are isomers and structural isomers, there is virtually identical mass fragmentation patterns, and therefore we can identify specific isomers. And as far as room temperature spectroscopy, we do observe overlapping spectra because of these band broads caused by vibronic, thermal, and inhomogeneous band broadening. So these methods really lack the selectivity towards the individual isomers in complex samples. This is an example of a published work involving those 10 high molecular weight PAHs shown in the previous slides. And as we can see, this is the RPLC chromatogram of a synthetic mixture of these PAHs, and it is observed that there are two pairs of co-eluting isomers, including benzo B-perylene, BB-per, and naphtho 1,2-K fluorantine. So these co-elute with very similar retention times, and we can visualize this here in the figure with these vertical lines where we can see that they overlap, and therefore they would co-elute if they were in a sample together. The same is observed for dibenzo AH pyrene, DBAHP, and naphtho 2,3-K fluorantine, or N23KF. We observe the same overlapping of these chromatographic peaks, and therefore they would co-elute in a sample. When we observe the absorption spectrum of these pairs of isomers, we can see, it's obvious to see that there is strong, these are the absorption spectrums of benzo B-perylene and naphtho 1,2-K fluorantine, and we can see them overlapped, their absorption spectra. When we overlay the spectra, we can see that there is strong interference at their peaks and in their absorptions, and therefore absorption spectroscopy would be very difficult to use to determine one of these individually in a sample that includes both due to the spectral interference. The same can be visualized for N23KF and DBAHP, strong overlapping, as well. So therefore, absorption spectroscopy would be challenged by this to determine an individual isomer. Excitation and fluorescence spectra of these are also overlaid, as you can see here. The excitation and fluorescence, they're overlaid for these same co-eluting isomers, and again we observe very strong overlapping of their spectra, making it impossible to determine one individually from the other. The same is true for the second pair of N23KF and DBAHP, so strong overlapping in their excitation as well. However, when we incorporate a mixture of these co-eluting isomers under Shpol'skii conditions at 77 Kelvin and 4K, we can see the increased sharpness of these peaks, allowing the individual determination of these isomers in a mixture. This is the overlaid spectra of N12KF and BB so we can see we could selectively identify by this fingerprint at 443 of fluorescence from that of 392 from the other compound, which we normally would not be able to do as shown in the previous slide. And this is exactly true for the second set, N23KF and DBAHP. At both of these temperatures, we see very sharp quasi-linear spectra that would allow for that selectivity that we need to determine these isomers individually. In conclusion, PAHs are environmental pollutants from both natural and anthropogenic sources. They're omnipresent, and the main source of these are anthropogenic sources, unfortunately. The EPA has provided a list of 16 PAH compounds, which should be routinely analyzed. And the chromatographic methods they provide include EPA method 50.1, which includes HPLC and UV-vis absorption fluorescence spectroscopy, and the GC method is 523.3. These are suitable for the analysis of these EPA PAHs, however, they are not suitable for the analysis of structural isomers in complex samples due to the broadening of the band structures. In this case, it would be good to apply Shpol'skii spectroscopy, which, as mentioned, involves the PAH molecules frozen in a solvent host, producing ordered polycrystalline matrices at very low temperatures. This minimizes band broadening due to inhomogeneous, thermal, and vibronic, and increases the selectivity of this method towards specific PAHs in complex samples. And lastly, we went over an application of Shpol'skii spectroscopy, which involves the analysis of structural isomers of high molecular weight PAHs, which are often much more toxic than lower molecular weight PAHs. And as we observed through the spectra and the example from that published work, Shpol'skii conditions provide sufficient resolution for the selective determination of these co-eluting isomers. I would like to thank Dr. Campiglia for allowing me into his lab and for all of his help and mentoring, as well as all of my lab colleagues for all of their mentoring. Thank you.